Good afternoon, ladies and gentlemen. Thanks for tuning in. It is a great pleasure to welcome you all to our third webinar in the Rain Enhancement Hub series, hosted by the National Center of Meteorology and organized by the UAE Research Program for Rain Enhancement Science, or UAE REP for short. My name is Yusuf Webby. I'm a program officer for the UAE REP, and I'll be moderating today's webinar. First off, I wanted to give a quick recap on our first two webinars, which discussed the background and emerging developments for operational cloud seeding, as well as the broader field of rainfall enhancement research. We specifically discussed the UAE's efforts in both fundamental and applied research in this field through its operational cloud seeding program, as well as the pioneering research conducted by the UAE REP project. In our second webinar, we showcased some important background and historical data on the UAE's rainfall regime and its variability over the past few decades. The key take-home message from the previous two webinars really boils down to the importance of high-resolution and reliable Earth observation data sets in this field. Towards that end, in today's session, we'll hear about the emerging applications of synthetic aperture radar, SAR, for monitoring changes in surface soil moisture, which in fact is a direct response or proxy variable for rainfall events, particularly in arid and hyper-arid regions. As such, we'll learn more how SAR technology can be leveraged for the evaluation of rainfall enhancement activities. Joining me today to share their insights on this topic are two distinguished speakers from Bayanat, a Group 42 company based here in Abu Dhabi, which provides AI-powered geospatial intelligence solutions serving multiple sectors. Our two speakers are Dr. Prashant Marpu, Director of the Space Program, as well as Dr. Marcus Mueller, Lead Data Scientist. Just a couple of housekeeping points before I hand over to our speakers to start their presentation. For our audience, please go ahead and type in your questions at any time using the chat box. We'll be sure to address your questions during the Q&A session after the presentation. I'll now hand over to Dr. Prashant Marpu to start his presentation.
Thank you, Yusuf. Are my slides visible now? Okay, great. Thank you. So we'll be talking about potential of high temporal resolution SAR images for mapping rainfall extent in hyper-arid regions like the UAE. So we wanted to get an overview of how SAR can be used in supporting the UAE rain enhancement program. So we put together some examples and a bit of background on how this is going to work. First of all, we represent Bayanat. It's a company which originally started as a spin-off from the Military Survey Department, was commercialized in 2008, went through different groups ownership from Mubadala, EDIC, and in 2020, G42 acquired Bayanat, and it is now being transformed into a geospatial intelligence and AI company with diversified AI capabilities like the Geo AI platform we are developing and extending the reach beyond standard data acquisitions, but also venturing into multiple sources like advanced sensors, drone-based sensors, underwater sensors, and so on. So to just get an overview, Bayanat is a G42 company which deals with geospatial and AI, but in the G42 ecosystem, which in itself started as an AI research and cloud computing company, so many things got added up over the last few years, especially during the pandemic, where G42 took a center stage in pandemic management in the UAE, set up facilities for testing and also a joint venture with Sinopharm to produce Hayat vaccine in the UAE. G42 operates over a variety of sectors, including analytics, healthcare, digital transformation, a joint venture with ADNOC to support their operations, financial AI and asset management, and applications development. But at the core of it is all related to AI development and cloud computing. The G42 cloud computing environment is the largest in this region, with data centers that will be up to 200 megawatt cloud in the coming months. We have two primary investors, Silver Lake, a US-based global technology equity firm, and then Mubadala locally, who also has invested in G42. So how Bayanath operates is it tries to acquire data from multiple sources, be it Earth observation from satellites or aerial surveys or stratospheric platforms, ground surveys, mobile surveys, and so on. Both in terms of images and non-imagery things like point measurements, for example, uh, using GNSS or RF-based systems and so on. On the top of that, we have the multi-intelligence platform, which supports in a lot of products and services such as maps, data products, and value-added services on the top with AI and data analytics included, serving a variety of clients. So Bayanath serves all the major government customers in this region, along with significant private players as well. We partner with almost all the satellite data providers that are providing data in this region as their local reseller. So we are also a bit data agnostic in the sense that we have multiple partnership with multiple data providers, so that we are always there in terms of supplying the data needs of our government customers. So at the core of this transformation of Bayanath when G42 acquired was the introduction of this AI platform development, which is a data agnostic platform that can serve multiple sectors. Basically, at the core of it is the AI engines, which can integrate multiple sources of data and can be used to develop variety of applications depending on the use of the customers. So as a part of this, as an example, what we're trying to do is trying to develop AI models for individual use cases as we build on the projects we are acquiring. So depending on the projects, basically different models are trained and continuously evolved depending on how much training data is available and how much training data gets available in the future. So the models continuously evolve, and this entire model studio basically keeps track of all these models and lets end users use these models on the top of the platform. Recently, we have started having a special focus on SAR. I mean, in the reverse order, actually, in this slide, the first one was the MOU with ISI. We started collaborating with the Finnish new space company, which offers a fleet of 16 SAR satellites right now. We have an MOU where we are jointly developing applications, novel applications that are highly relevant for this region, both in urban applications and other applications like the one we will see today. We're also setting up a joint venture with ELTA, a subsidiary company of Israel Aerospace Industries, to have a dedicated SAR application center, um, primarily focusing on land subsidence and change detection applications, along with marine applications. Now we are extending that to cover many more novel applications on SAR, but we'll start with the land subsidence and change detection applications with that platform. So Bayanath has also invested in developing HAPS solutions. So HAPS is a platform that stays in stratosphere at around 20 kilometers, thereby providing opportunities to have continuous monitoring and long endurance from very low altitudes, unlike satellites which are around 400 to 1,000 kilometers in the LEO or 36,000 kilometers in the GEO planes. So with this is a preliminary work that is invested in developing this solution that will be flying in a few weeks over UAE. and will evolve to host larger payloads in the coming years. So with that introduction of the company, I'll get into the topic, today's topic on using synthetic aperture radar for soil moisture measurement applications. So SAR is sensing in the microwave part of the electromagnetic spectrum, which is roughly from around 1 centimeter to 1 meter wavelengths, basically, with different bands. In microwave sensing in general, we have two types. One is active sensing, where we use our own source, for example, with the SAR, where the system sends its own pulse and then sees what is coming back. We can also have passive sensing because the Earth uh, emits radiation in this region as well. So radiometers in space can detect what is being emitted from Earth, and based on that can infer certain properties of the surface of the Earth. So most of these satellites operate in X-band for high resolution, and C and L bands, for example, for slightly lower resolution, but where we require applications with penetration requirements, basically. So uh, we'll have a few centimeters of signals that can go into the earth as well, depending on the wavelength of operation. SAR is an active system, as I said, which illuminates the Earth's surface and measures the reflected signal. So the core of it is of the synthetic aperture radar concept is that it's like it uses a smaller antenna, unlike regular radar systems, which would need much larger antennas at these frequencies. The key part is that it's like the point on Earth, any point on Earth will be illuminated by the beam by multiple beams as the satellite or the flight goes in its path, and from that we can kind of create a synthetic aperture which is much larger than the actual swath size or beam size. That way we can do with smaller antennas because it's like theoretically we are creating a larger aperture. Images can be acquired day and night because of using its own source, so it's completely independent of solar illumination, unlike the optical and near infrared sensors. The good thing about synthetic aperture radar is that microwaves are kind of transparent to the atmosphere, in the sense they can penetrate through the atmosphere, clouds and dust, for instance. So irrespective of the weather conditions, if it's cloudy or dusty, you can acquire satellite images with SAR. So as I said, it's like these are the advantages. We have nearly all weather capability, day or night capability, because we're using our own source. It has penetration through the vegetation canopy to a certain degree, depending on the frequency of operation. Penetration through the soil to a certain degree, depending also on the frequency of operation. Minimal atmospheric effects, because the atmosphere is more or less transparent at these frequencies. It's highly sensitive to dielectric properties, which means that we can distinguish between different surface properties like soil moisture, if it is liquid or frozen water, or floods or high moisture content in the soil, and so on. It's also it's also sensitive to the structure, in the sense the geometry affects a lot in how much of the signal comes back. The backscattering depends a lot on the surface roughness, and also the geometry of the objects on the ground. SAR alone may not be useful in certain applications, but it can provide complementary information to optical data. Uh, on the other hand, SAR has its own applications which optical data cannot provide as well. So this is an example radar image over the UAE in the desert, which shows sand dunes and a small agricultural area in the south of UAE, close to the Atlantic water. Um, as you see, it's like what happens is if you have a flat surface, the signal comes, hits the surface, and goes away, basically. So there's no return. The radar image looks dark. If you have a slightly rough surface, Some part, a small part of the signal just comes back as backscatter. So you'll see a very gray or darkish gray type of return in slightly rough surfaces. And if you have high surface roughness, you'll start seeing a speckle effect, like salt and pepper effect, basically, on the image. If you have a forest, highly vegetated area, it's kind of a random scattering. Um, so you kind of see random uh, returns on this thing. If you have a cropland, you can see those organized kind of dipole scattering, because each plant in the crop basically scatters the signal back in an order. Mountains show various type of characteristics depending on the slope of the mountain. We can have various effects such as foreshortening, overlaying, and all those things depending on the height of the mountain and the slope of the mountain. In cities, we often see, these double bound scattering where the signal basically hits through the walls, goes from the roofs and comes back with significant intensity. So you see bright regions, especially near the walls. You have shadows on the other side, and the rooftop basically is dark as well, because the signal just goes away there. It doesn't scatter back. So depending on the frequency, as I said, it's like for smaller wavelengths, it comes off from the surface. For slightly larger wavelengths like L band, it penetrates through the canopy. In this case, through the vegetation, for example, X band comes from the top of the leaves. C band hits the stems, branches basically, and L band can go deeper as well. For example, can also hit the ground below. So if you want to detect, for example, a car sitting there, L-band radar might pick up that strong reflection from the conductor there. The same applies to dry snow. When it is with different frequencies, the penetration is different. For wet snow is completely different as well, because the dielectric properties changes there. So you'll have high reflection from the surface, and so the penetration will be a bit limited there. The same applies to dry sand as well. Um, so that's why I know C-band and L-band satellites have been used for archaeology applications, because they penetrate a bit into the soil there. So when you have a wet surface, because of the dielectric properties of the surface, we will see a strong reflectance or strong scattering from the surface. But if you have a flooded area, for instance, it becomes a specular reflection, in the sense the signal is going away from the sensor, so there's no return. So, for example, if you have a rainfall event and if it's flooded, the areas that are flooded appear dark on these radar images, but the areas that have wetness, or those areas that are not flooded but have significant soil moisture, reflect brightly. So this is a very good indication to differentiate between flooded areas and wet areas compared to dry areas, basically. If you have a bit of vegetation like marsh in the flooded areas, for instance, you'll also see returns because of this double bound scattering. But if you have dense vegetation, nothing changes, even if you have water below there. So, how does soil moisture sensing works? Basically, it's like there are two types of methods. The in situ methods are often used to carry out these measurements. They can be gravimetric techniques or nuclear techniques, EM techniques, hygrometric or tensiometric techniques, depending on what types of devices are used and what exactly we have to measure, either the topsoil or more deeper into the soil and so on. But then this needs, like, these are point measurements that are carried out in the field and needs a lot of effort to set up all these things. On the other hand, remote sensing methods offer a remote application of sensing and can detect moisture in wider areas. Um, microwave sensing is often used for soil moisture estimation, but there are also applications in using visible and near infrared and thermal IR as well, which measures surface temperature and reflectance uh, to look at the changes and see how if you can model soil moisture from that. In the passive microwave, we look at the microwave emission of the surface or the brightness temperature that is measured at the sensor. In the active microwave or radar, we use the backscattering coefficient or the dielectric properties to infer soil moisture from these measurements. So, as I said, in optical remote sensing, we look at the reflectance of the signal that is coming back, and then it's area specific. So, soil moisture can be modeled as a function of reflectance of dry soil in that region, roughness of the soil there, spectral properties, illumination information, and amount of organic matter that is present, like the vegetation and so on, um, and the soil texture. So if you know roughly these parameters, you can actually develop a model that can infer the relation between the reflectance and the soil moisture content in optical remote sensing. But this is extremely tedious to get all these parameters, and moreover, it doesn't work when you have clouds. Thermal sensing again doesn't work when you have clouds, but again offers a nice alternative to optical remote sensing here, because whenever uh, the soil has moisture, the thermal conductivity of the soil and the heat capacity of the soil changes, and the thermal inertia basically changes accordingly. So this is directly related to the changes in the surface temperature uh, between day and night, for instance. So if you look at the maximum temperature during the day and minimum temperature and take the difference between them, this is an indicator of thermal inertia, and this changes with changes in soil moisture. So you can develop models where you can infer soil moisture content by looking at the variation in the surface temperature. And in microwave part, we have the two sensing ways. As I said, like radiometers measure the passive microwave signal that is coming from the Earth's surface, which is largely depends on the emissivity of the surface. And the emissivity of the surface basically changes with the soil moisture. So if you measure the dry soil brightness temperature, and look at the change in the brightness temperature the following days, for instance, then this can be modeled with respect to the change in emissivity. On the other hand, with the radar, the backscattering sigma naught is directly dependent on the dielectric properties of the soil. Of course, the geometry and system parameters are important, but if you're roughly measuring the signal with similar acquisition geometry, for example, the look angle and the time, basically, it more or less directly depends on the dielectric constant of the soil, which has a direct relation to soil moisture. So this is how it works. So the fundamental reason, as I said, why microwave remote sensing is able to provide soil moisture information is this big difference between the dielectric constant of water, which is around 80, and the dry soil, which is around 4. As the soil moisture increases, this dielectric constant increases rapidly, and that changes are reflected in the reflectivity of the surface, which is gone by these Fresnel equations. Again, depends on dielectric constant of the surface, viewing angle, and polarization. So if you are measuring at the right polarization and the right viewing angle, only the dielectric constant is varying. And by looking at the dielectric constant, we can infer how much percentage of soil moisture is there in the soil. So dry soil normally has low dielectric, as I mentioned. The saturated soil with moisture has high dielectric. Moist soil with a bit of vegetation on the top has moderate dielectric, and uh, the kind of frozen soil basically has variable dielectric depending on the properties at the surface. Again, dry soil has low dielectric constant, but the variation of dielectric constant with respect to soil moisture differs from soil to soil. So this has to be modeled independently as well. For example, clay increases, the dielectric constant in clay increases significantly as the soil moisture increases, but in silty soils, basically, it's not as rapid as we expect for clay. So this has been studied a lot in literature, actually. It's like over the last 2 decades, soil moisture estimation from microwave sensing, especially SAR, has been documented, say, with high accuracy. But the utilization of such technology in mapping extent of rainfall has been limited till now, largely because of two reasons. Because most of these products, standardized products that are available, are low spatial resolution, because they're primarily coming from radiometer-based products. And the radar-based products have insufficient temporal resolution, because most of these radars, high-resolution radars, are in low Earth orbit, which means that the revisit period for any satellite to come back to the same location is around 7 to 15 days, for getting the resolution we need, basically. So because of this, this was not actively used in a lot of rainfall assessment applications. But there's huge potential with respect to the science that is already documented in terms of measuring soil moisture with very high accuracy. These are some of the products that are already available. As you can see, focus on the grid spacing here. Most of them are, like, you're talking about degrees or kilometers, basically. These are mostly coming from uh, passive sensors on board, and the active sensors based detection basically has low temporal resolution as well. So this is an example of what I wanted you to focus on, was this accuracy, basically. Most of these products have been documented to provide significantly high accuracy compared to other products, in a way, or other type of applications, in a way. So you see, as I see now, it's like there is significant potential in utilizing radar for soil moisture retrieval. With this, I'll hand over to Dr. Marcus, who will show some of the results we've been acquiring with radar images, or UAE, to show the potential of how we can actually utilize this for supporting the rainfall enhancement program.
Hello, good afternoon. Many thanks for the introduction, Dr. Prashant. Yeah, let me just pick up from there and continue right away. Next slide, please. Yeah, so that's my topic. What's the opportunity? I'm talking about SAR constellations. As Dr. Prashant already pointed out, SAR is not a new technology. We already have SAR satellites and the whole sensor technology for a few decades. The problem is resolution. So both temporal as well as spatial resolution is needed to be relatively high in order to make sense of these rainfall events, especially here in the UAE, where we have only like 2 or 3 events over the year, and then so after the event, the soil moisture is gone very quickly. So you either get some images in that measure that signal, or you don't measure anything, which is a real problem, which can be solved by recent microsatellite constellations, as they like to be called. Companies such as ISI and Capella are now shooting satellites in the orbit, like fleets of satellites, which allows us to get much higher temporal as well as spatial resolution of these data sets. And we expect the temporal resolution to come down to a few hours for each spot in the Earth, on the Earth, in the coming years. Next slide, please. I want to talk mainly about ISI because Dr. Prashant already mentioned it. We got MOU with them, so which means we are doing R&D activities together with them. We have access to data and to the know-how of the analysts, which is great. And right now, the other reason is quite purely that ISI operates the world's largest commercial constellation of SAR satellites. So for 16 satellites, further, they will expand the constellation further in the coming years. I think at least 4 more by mid this year. And then they want to get an average time, a revisit time, like potential revisit time of around 3 hours, which is pretty amazing. So they offer different products, spot, strip, and scan, which relates to different sizes of images and resolutions of these images. I will later on show an experiment with a strip image. And yeah, on the right, you see some more specifications. Dr. Prashant introduced different bands. So we are operating here in X band, one polarization only. And but the really like the golden product of ISI is what they call DCGTR. That's a mouthful. It stands for Daily Coherent Ground Track Repeat. And what this is about is they not only offer that you can get a daily revisit, like you order images and you can get an image for every day. No, for this specific product, they even guarantee that it's coherent. So coherent SAR imagery allows like these advanced applications that make SAR so attractive. So for example, you can look at land deformation. And in this context that we are looking right now, you can have change detection, which is very, very detailed, really picking up very small changes. Next slide. Yeah, and that's what we started with these experiments was we simply wanted to see if we can pick up soil moisture in areas in areas of the UAE. We started with Sentinel-1, which is a freely available an open sensor, 10-meter resolution. But you know, it's a good starting point to check out what you can do. What you can see here is a visualization on the left side of a combination of 2 SAR images. So the principle is quite simple. You take an image, like a reference image, taken where it was dry, and then you take an image where you had shortly before a rainfall event, which is supposed to be moist. And if you combine them in a specific way in this visualization, like wet areas would be picked up in red, and you see that quite nicely. On the right side, you see an optical image purely for comparison purposes, so you can see how the landscape looks like. It's not taken at the same time, but you can see a dune landscape and these 2 mosques in the middle near Al Dahid. Next slide, please. Another example where the SAR image is not really so clear, but I like it anyway because this is a dam in Fujairah. Again, Sentinel-1 data, a coarse spatial resolution. On the right top, you see the optical image again. By the shadow, you see that there's a dam. On the bottom, we even have a photo of the dam. And on the left, again, this SAR change image. And it's quite nice to see that on the one side of the dam, the soil moisture is picked up in this difference image. So again, we find what we are looking for. Next slide, please. And after this, we became a little bit more courageous and we thought we'd do some experiments with tasked imagery. So what we did was, first of all, we waited. We waited until the weather forecast told us, so in the next coming days, there would be a rainfall event, which is always a little bit of a lottery, but we needed to take that risk, I guess. So before this weekend in February, where there was a rain event forecast, we tasked 3 images. The first one before the actual rainfall, and then 2 more images during the predicted rainfall. And these are strip map images, as mentioned before, at 3 meter or 2.5 meter resolution, tasked them over the Northern Emirates. And if you look at the images, at these intensity images right now, apparently you don't see any differences. if you just look at the intensity. And then we were lucky because, if I remember correctly, there was a strong rainfall during the night from the 12th to the 13th, and then light rainfall from the 13th to the 14th. Which brings me to the next slide. Here again, we did these change images. So each of these 3 images we compared to a reference image. And what you see here, like, first of all, what you need to ignore is the very red area in the eastern parts, because that's where the reference image did not cover the same area as these images that were taken. But overall, what you see, especially outside of the mountainous region, is that from left to right, the area is first getting more blue-greenish, and then less blue again. And here in this visualization, that indicates soil moisture. So even at that scale, and it's not super clear at that scale, you can already see that we pick up a signal, that we pick up these changes in the dielectric constant from space, which is nice. Next image, next slide. Same as before, just a little bit zoomed in. This is Ras Al Khaimah, where you can see again on the left one, the first image before the rainfall event, very dark, especially, so basically we didn't pick up any soil moisture. Then on the 13th in the morning, quite clear indication that there was rain, and on the 14th it dropped, but it's still there. Next slide, please. And this is exactly the same, just in a more urban area. Again, the same area, the same time, just for visualization. In the middle, you see soil moisture picking up. Next slide. And here we are already at the end. Very quick summary. So first of all, SAR imagery allows you to map soil moisture reliably. Reliably means you can pick up the signal from space. With the new SAR satellite constellations, we even have the chance to really get the images in at the right spatial resolution, but especially at the right temporal resolution, because you really need these images like a day, or even better, a few hours after the rainfall event. So ISAI, for example, provides imagery that can well be used for that. And with these early experiments, I mean, we are far from any productization, but what we're looking for is right now is the signal getting picked up in these images. And in this regard, the experiments worked out pretty well. They prove that we can pick up the soil moisture changes in the SAR images, which allows us in the future to go into model development, developing some smarter methods to pick up where the rain actually fell. And at some stage, you want to validate it and combine it with in situ measurements. And with that, we come to an end. Thank you very much for your attention.
Thank you very much for the insightful presentation, Dr. Marcus and Prashant, and the very interesting results from the case study. It really shows how much potential SAR has for the region here, particularly for rainfall monitoring. We've received quite a few questions from our audience to tackle during our Q&A session happening now over the next maybe 10 minutes. So I'll welcome my panelists back to the stage. Right, so some of these questions are more technical, but some are also more data management, I think looking more into the future where this can be applied moving on. So the first question is, can G42 or Bayanat provide support in making this SAR imagery available to academia and the research community, maybe specifically for soil moisture, at least for local institutions within the UAE? Maybe Prashant?
We are working on that. We are working on that. Once we are done with our own analysis, basically, some of those data sets will be available for the academic community here. We'll work on that. It's like for now we can look at case by case requests, but at some point we will open up for the NCM community.
All right, thanks, Prashant. The next one is, what are some of the challenges you see for using SAR data for the evaluation of rainfall enhancement efforts, or more generally for hydromet studies? I think the presentation really focused on the strengths, but maybe we can start to look into some of the challenges, and that will also help, forge partnerships
So
and so
yeah,
on.
so there are two things now. Basically, first of all, it's very very clear that it's like SAR picks up soil moisture changes. No, as a starting point, just to map the extent of changes in soil moisture, this is more than enough. No, so that's what Dr. Marcus is working on, to look at soil moisture changes and mapping the extent as a starting point. Okay? But in terms of measuring the actual changes, actual values, then you need to come up with some model development. So the standard approach of getting in situ measurements, mapping back to the signal changes we have, uh, looking at types of soils, for instance. For example, we already have a very nice soil map available for the entire UAE at high resolution. We could leverage that to start working on developing models for different soil types. And once that's there, basically, we can also probably more accurately measure the content, soil moisture content as well. That could relate back to amount of rainfall if we can work it out. Basically, should be possible. It's been done before, but again, it needs to be adapted to the local conditions here.
Indeed. Another question from Mr. Samer Takidin. He's asking if these images show where the water is dropping or where it's moving towards. I think it's both, essentially, depending on where you are, but Prashant, you can
Exactly. No, so the thing is, it doesn't tell you the level of the water. Now, for example, if it is water before and water after, you don't see, because it's a specular reflection, it goes away. But if it is change in the soil moisture, for instance, or a dry soil becoming flooded, then you can actually map it with radar.
All right. The next one is very technical for rainfall enhancement, but Prashant, I think you can handle this one as well. Cloud-based heights in the UAE are roughly 3 to 4 kilometers above ground level. So a large fraction of rainfall through cloud base is already subject to evaporation through the course of its travel path until it reaches the surface. So how can we account for this uncertainty when looking to evaluate these seeding operations from ground-based
So
sources such as
it's like yeah, there are two parts of this. No, anyway, it's like we using the radar itself. We cannot provide a full solution anyway. It's just that we get one part of the water budget there. If you apply the right, if you get through the right models and apply the right approaches, we get the soil moisture content. So that's one part of the water budget there. And then if you can combine with other in situ measurements, to look at the total water content in the atmosphere, basically, the changes there, can reveal some of these interesting patterns, and they can help us in developing more advanced models now. So it's two sides. It's not straightforward. Radar is not going to provide full solution there, but you need to combine this plus other sensors to come up with more intrinsic models there.
All right, I think this leads into a very interesting question now on AI. So when it comes to rainfall enhancement science, how can AI be integrated to improve operations? So I think he's alluding to data fusion with SAR. So we've discussed this, I think, offline, but it would be interesting
Yeah, I
for
know.
our audience to
I
learn
mean,
how
we,
we can
we, we, we also had a presentation, I think, during the last UAE Rain Enhancement conference last year, where Talal was talking about this thing. So both sides, it's like, for example, converting, numerical weather models into AI-based models is a very interesting application that we started working on, very early days, but some initial results show some promise. Basically, what we are trying to use the AI muzzle we have, the high performance computer Artemis we have in G42, to kind of make a black box AI model by feeding it with results of numerical weather models now. This is one thing we are working on, but in the end, it's like any model development, any AI model development is basically uh, garbage in, garbage out. If you don't put in the right things, in basically. So that's where we also need to work closely with actual experts, not treat it like a black box, but we also need to make sure that we feed in the right variables as well. There is a lot of potential, at least from my own understanding of how things are working, my limited knowledge, especially on some of these things, even if I was involved a bit for a while. But there is a strong potential in actually developing significant AI models for this thing, because once a proper AI model is developed and validated, then the inference is super quick. You don't have to wait for hours of simulations to give you results. The inference will be like few minutes basically. If that works, and you can actually readapt the models by training more and more with time, I think we'll be at a decent pace at some stage where we can have these forecasts in a couple of minutes rather than couple of hours, and that will help furthering the cause for the rain enhancement program, for instance, and other applications which require numerical weather prediction.
If I may add to that, I believe not only in the modeling itself, but also in the context of data mining, AI can play a role. So the relationships between all these climatic variables are extremely complex, and the physics are really complicated. And quite often we don't understand how they relate to each other. So machine learning can play a role in figuring out what kind of relationships exist, which can then lead to a better physical understanding in the end of the processes.
No, indeed. I mean, the question was set up in a very nice way, so that was an easy one to tackle. I think the next one also for Dr. Marcus, you mentioned some in the summary slide, some areas of future work maybe. So the question is, how reliable is SAR data for quantitative soil moisture measurements, so per volume basis, as opposed to its qualitative application for change detection? And has there been any field-based validations done? And if not, would you see these types of field campaigns as a priority to demonstrate SAR imagery here in the UAE? And maybe I can just add one thing here, that NCM actually, as we speak this week, have been deploying soil moisture probes, basically TDS gravimetric probes on about 16 of the weather stations. So we'll have some of that data coming in. So if we can combine that with some trials and validation, that would be very useful. But how would you see that as a priority for the technology for this region?
Yeah, I mean, it's quite clear. Like what we are looking right now are the spatial patterns. So what SAR allows you is essentially, spatial upscaling of point measurements. So that's cool. That works reasonably well. If you really want to go into measurements, you already answered the question yourself, Yusuf. You need to combine it with in situ measurements and calibrate these models. It doesn't work any other way.
Indeed,
yeah. So it would be very interesting, Yusuf, actually, to you do these measurements or set up these stations with respect to the soil maps. There's no point in having the stations in the same soil types, basically. If we were to use radar data in the future for such applications, since it's highly dependent on the soil type to develop the model, so you go back to the soil maps and basically place your stations according to the soil types.
This was a great discussion, a lot of technical details, as well as some interesting areas of future work. Maybe just a final wrap-up question, just to summarize and maybe consolidate everything. So what areas or specific research questions do you think that Bayanat can collaborate with UAE Rep or NCM in order to increase the efficiency of cloud seeding operations? So we spoke a lot about I think we already answered the question, but just having maybe some high-level research questions would be useful to wrap up the discussion from both of you.
Yeah, I know. It's like I would say anything geospatial now. Now that Bayanat is transforming from a data acquisition company to a value-added AI company, basically. Anything geospatial. The platform we are developing is data agnostic and application agnostic, basically, depending on the end users. The entire platform can be customized to deploy to certain applications, basically. So it already comes up with significant resources on the cloud and so on. So that will be very interesting to look at basically. And all these novel applications we're talking about with these new data sets that were never available before and are becoming available because of this new space concept, with the constellations. It will be interesting to actually start working on integrating these things into the program through joint work, basically, in terms of developing these models now. So that's my 2 cents, basically. But anything geospatial, if you want to answer that thing, we'll try to work with you guys on setting up whatever is needed, because that's our objective or mandate actually, to work with the government agencies and enhance the capabilities here in the UAE.
Exactly, it's all about the spatial extent of these events, and it's about upscaling point measurements to make it very simple, to boil it down into 2 sentences, 1 sentence.
All right. Maybe just one more comment from our audience, Dr. Ali Abshayev from Russia. We already discussed a lot of the challenges, so he's chiming in here on the. So one source of uncertainty would be that soil moisture in the UAE can also occur due to nighttime condensation of water vapor due to a sharp drop in temperature. So that's associated with the fog events that we get, of course. So how to separate this from precipitation? Again,
Yeah,
I think that applies to a lot
it's
of
again, it's we have to continuously monitor that, basically. So if the temporal resolution increases, basically, so you can probably separate that. If you look at the same area in a few hour intervals, basically, and if the condensation is timely independent, temporally independent to the precipitation event, then you can still figure out. Okay, but if these events happen between the two acquisitions where you're comparing with, then you cannot separate them, because in the end what we are measuring is the amount of moisture in the soil. If you increase the temporal resolution and can separate them out, then it's possible, and that would be possible in the future actually with these constellations. As we said, in 1 year period, basically, ISI will have the capacity to offer 3 to 4 hour resolution, temporal resolution. Other satellite companies are building up their constellations as well, like Capella and other things. So it's possible in the near future. In, let's say 1 year is a near future, basically. So that's so that should answer your question there.
All right. I'd like to thank you both very much, Dr. Prashant and Dr. Marcus. This was an extremely insightful presentation, and it really opens up a lot of future work for the community on SAR data specifically, and gave us a lot of exposure on what Bayanat and interesting work you're doing here. So thanks again to our audience for tuning in. This webinar was recorded and it will be on our website if you missed anything and you want to revisit. I encourage you all to tune in for our fourth webinar, which will be coming up soon, and we'll announce it on our channels. Thanks very much, and have a good day or night, everybody. Bye.